All right, welcome back, everybody. So today we are going to finally talk about support vector machines. And this is a way of performing classification that has a rich history, lots of beautiful theory, and was one of the main, most widely used classifiers for many, many years. I think in recent years, people tend to opt more towards neural networks, but there's a lot of important concepts that show up in support vector machines that are worth knowing and understanding. So to get started, I want to go back to last week when we talked about ridge regression. And if you recall, we said that the learned weight vector with ridge regression had a particular form. So we first derived it from a regularized least squares perspective, but then we started thinking about how to interpret it using the singular value decomposition of X. So we're going to think about our feature matrix X as having singular value decomposition U sigma V transpose. And then we can write the ridge regression weight vector as V sigma transpose U transpose times U sigma transpose plus lambda identity inverse times U transpose Y. So this was the form that we derived at the end of class last week. And we can factorize this into two components, where the first component, right here, this is simply X transpose, right? If we look at the singular value decomposition of X and we take the transpose of both sides of this equation, then we get U sigma transpose U transpose. And then everything else here, we just call alpha. So we are defining alpha, the vector alpha, to be this product. And if we think about what's happening here, we are taking the vector of labels y from our training data. Then we are applying this orthogonal transformation. You can think about it perhaps as a rotation. Then in that rotated space, we are reweighting each one of the coordinates, and then we're undoing that rotation. Okay, so the other point that we talked about last time is that this vector, or this representation of W hat R as X transpose times alpha tells us that this weight vector is equal to a weighted sum of the columns of X transpose, where the alpha i's are the weights. And if we think about, well, what are the columns of X transpose? Those are actually our features. So this is a weighted sum. So the columns of X transpose are the rows of X. So this is a weighted sum of our training feature vectors, the Xi's, with the alpha i's as the weights. So this is giving us a new perspective on how to interpret the ridge regression weight vector. It's just a weighted sum of our training samples. And this expression for alpha is telling us how to compute those weights. It depends on the labels. So we're going to give different weights to different samples depending on what their label is. But we're using the SVD to figure out what those weights should be. Okay, so I can similarly and maybe more efficiently write this because I can take this vector alpha, and what I can do is I can move, remember that U transpose is equal to U inverse with the singular value decomposition. So what I can do then is I can actually move the U's into this inverse matrix. And I can write alpha now as being equal to, I'm going to have, just want to make sure I get it right, yep. U sigma, sigma transpose, U transpose, plus lambda U transpose, inverse, times Y. And this is useful because now I can actually, this is still identity. But now I can think about this in terms of X. I can write this as X transpose plus lambda identity inverse times Y. So putting the pieces together, if I come over here, we have that our ridge regression weight vector is equal to X transpose alpha, where alpha is equal to X transpose plus lambda identity inverse times Y. Okay. So we derived that last time. And then we said, not only is this very good for doing linear classification and linear regression, where we want to think about weights on our various features, but also we can think about mapping all of our features to a higher dimensional feature space. So in particular, we said, imagine that we have a function phi that inputs a feature vector x and maps it into a new space. So our feature vector x, as always, is p-dimensional, but this phi function can map it into something where often the new dimension of phi of x is higher dimensional than p. And so as an example, we could have, for instance, that phi of, well, let me just do an example where I've got two coordinates, x1 and x2. What I could have is that would give me a new vector that's, say, x1, x2, x1 squared, x2 squared, x1, x2. So now what I've done is I've gone from a two-dimensional feature vector to a five-dimensional feature vector that's capturing quadratic relationships or quadratic functions of my features, not just the raw features. And what we said is that once we've done that mapping, we can actually think about doing ridge regression in this new feature space instead. And so to do that, we defined a new matrix, capital Phi, which is going to be our new feature matrix in this high dimensional space. So the first row would be phi of x1 transpose. The second row would be phi of x2 transpose, all the way down to phi of xn transpose. So this matrix now still has n rows, just like before, but now it's got D columns, so it's much wider potentially than the original X matrix. But now we can start thinking about ridge regression using this. So we can say, in this new high-dimensional feature space, we can think about doing ridge regression, where now our ridge regression weight vector corresponds to the argument or the weight vector that minimizes y minus phi times a set of weights, 2 norm squared, plus lambda times the 2 norm of the weight vector squared. So it's just like before, only instead of using our raw feature matrix X, we're using this mapped feature matrix phi that has these more complex relationships embedded. But our work is basically done. We can actually take exactly the expression for the ridge regression predictor that we derived for the x space and just plug in phi instead. So now we would have that the weight vector that we seek is going to be capital Phi transpose times alpha, where alpha now is going to be equal to phi transpose plus lambda identity inverse times y. So exactly the same concept. We've just essentially done a little pre-processing step to our features before we solve ridge regression. So are there any questions about this so far? Okay, so I want to talk a little bit now about dimensionality. So in particular, when we did ridge regression before, remember we interpreted our weights, our weight vector, as being a weight on each one of the different features. So this weight vector was a vector in our P. And now, when we're in this higher dimensional feature space, our ridge regression weight vector is in our D. And there are many settings where D can be extremely large. Just as an example, right? Imagine that my original features are, say, 100 dimensional. And then I want to do this quadratic mapping. So then D in that setting is going to be like 100 squared or 10,000, right? So I've immediately, by doing this high dimensional feature mapping, gotten to a space where my weight vector is huge. And this is, even what I just described is still relatively low dimensional. And so what we're going to do now is we are going to talk about something called the kernel trick that's going to allow us to compute these sorts of predictors, but sidestep having to compute things explicitly in d-dimensional space, which could be huge. So this is going to give us some real computational savings. It also leads to some really beautiful theory. Define a kernel function lowercase k. And what that function is going to do is it's going to have two inputs. Let's just call them xi and xj. So two different feature vectors. And what this function is going to compute is the inner product, phi of xi transpose times phi of xj. So in a little bit, we're going to see that there are many different kernel functions that we can use where we never explicitly have to compute this phi vector, where we can just directly compute this inner product very efficiently. And I'll give you some explicit examples of it in a little bit. But for now, we're just going to assume that we have access to this kernel function and talk about what we would do with it. So in particular, we can also define the kernel matrix, capital K, so that if I were to look at the ijth entry of that matrix, it's going to be equal to my kernel function applied to features xi and xj. So I can take every pair of feature vectors that I have and compute the inner product in this phi space, or compute this kernel function, and use it to populate my kernel matrix. So just to be really explicit, this inner product here is just a scalar. It's just a number. And when we form our kernel matrix, we're going to have one entry for every pair of feature vectors. So this matrix will be n by n. It scales with the number of samples that we have, but not with D or P or anything about the dimensionality of those samples. Okay, so the reason that I'm bringing this up is because what we can show is that K is equal to capital Phi transpose. And if you're not convinced, you can just map out, using the definition of phi, what each entry of this product would look like and verify for yourselves that it will be equal to these different inner products. So what that means then is that we can actually write our ridge regression weight vector in terms of this kernel matrix. So it's equal to phi transpose times alpha, where alpha is equal to this kernel matrix plus lambda identity inverse times y. So we could be in a setting where computing individual phi of x's is hard, but computing the kernel matrix is easy. And again, I'll show you some examples in a minute. And once we've got that kernel matrix, we can figure out what alpha is. We can actually figure out how much weight we should be giving to each one of our training samples using that kernel matrix without doing anything explicitly in this feature space. All I need is this n by n kernel matrix. And in particular, once we have this, for a new, let's say, test feature vector x, we can predict a label as follows. So if we think about, in general, what we'd like to do, we are going to take this ridge regression weight vector and compute its inner product with phi of x. So let me just give myself a little bit of space here. I'm going to say that what we want is that y hat is phi of my new feature vector x transpose times w hat r. So now let's think about what that looks like. So I'm going to keep this, actually, you know what? I'm going to write it the other way. It's just going to be a little bit convenient in a second. I'm going to say w hat r transpose times phi of my new feature vector x. Now what I'm going to do is I'm going to plug in my expression for w hat r. So this is going to be alpha transpose times capital Phi times little phi of my new x. And if I think about what that means, that is equivalent to looking at the sum over all of my training samples. And for each one, I've got a weight alpha I. And then when I think about what this product means, what I'm doing is I'm looking at the ith row of phi, inner product with phi of x here. So what I have is phi of my ith training feature transpose times phi of my new test feature phi of x. Now, when you look here, you see that in this expression, we just have the inner product of two different phis, or phi mappings. And so I can actually write this using my kernel function. So I've got the sum from I equals 1 to n of alpha I times my kernel function applied to the pair xi and my new test feature x. So if we think about what's happening here, let me get another color of chalk. If we think about what's happening here, I'm saying that once we've computed our kernel matrix and we've got this kernel function, I can take my training data and I can compute this vector of weights alpha. And this is, again, a length n vector. This has nothing to do with dimensionality p or d. I'm just having this length n vector that's telling me how much weight I should be giving to each one of my n training samples. Once I've got that weight vector alpha, then when I get a new test feature vector x, I also don't have to use this phi mapping. I rather just compute my kernel function for every training sample and my new test feature vector, and I compute a weighted sum of those outputs of that kernel function where the alphas give me the weights. So I've got this sort of two-step procedure here, where first I'm computing this alpha vector, and second I'm making predictions. And both of them I'm computing only using my kernel function. And if I can, I'm saying that the kernel function is equivalent to this inner product in phi space. But what I'm going to show you very soon now is that I never actually have to do any direct computations in phi space. I can just do everything using this kernel function. Are there any questions so far? Yeah.
You're saying that we do all the computation with respect to the kernel function, but that's based off of the phi space. So, like, are we going to be given what the kernel function looks like?
Yes, let's do that right now. Okay, so let's talk about kernel functions. There's a lot of beautiful theory here that says, well, that would tell us like what gives us a valid kernel function. But for this class, I'm just going to show you some very commonly used examples. And I'm going to start off with an example where my feature vector x is in 2D. So in particular, it's got elements x1 and x2. And then I'm going to think about a setting where phi of x is x1 squared, square root 2, x1, x2, x2 squared. And so now if I look at the inner product of phi of xi and phi of xj, then I will get xi1 squared, xj1 squared, plus 2 xi1, xj1, xi2, xj2, plus xi2 squared, xj2 squared. Now, this is the same as xi1, xj1 plus xi2, xj2 squared, or quantity squared. And this is the same as xi transpose xj, quantity squared. So mathematically, we can think about this as doing this nonlinear mapping to a three-dimensional feature space and then computing an inner product in that 3D space. But it is exactly equivalent to just doing the inner product in my original 2D space and squaring the result. So in terms of how much computation I'm doing, these things are totally different, even though mathematically they're equivalent. So let's think about some more general examples. Oh, first of all, are there any questions? Okay. So, some popular kernels. First of all, we can have polynomials of degree q. And so in particular, I'm going to say that my kernel function k for a pair of feature vectors xi and xj is simply going to be this inner product xi transpose xj to the qth power. So it's just like our quadratic example, but we can do higher order polynomials. So this is a nice example because if I was actually going to compute, if I was to think about what the corresponding phi was, where I'm mapping a vector x to all of the corresponding cubic monomials, that vector, then in this case, d, the dimension of phi of x, would be roughly on the order of p to the qth power. So if my feature vectors p were 100-dimensional and I was going to do cubic polynomial, then the implicit dimension of the phi vector would be 100 cubed. It would be very high dimensional, but I only ever have to compute inner products in my 100-dimensional space. Another thing that we see is polynomials up to degree q. So if we think about what we did over here, every expression in this vector was exactly quadratic, right? But you could imagine saying, well, I want all the quadratic monomials, but I also want the linear ones, and I also want 0th order. And so we can alternatively say, let's let this kernel function between two vectors xi and xj correspond to taking that inner product xi transpose xj, but before taking it to the qth power, just adding a 1 to it and taking that to the qth power. So very simple change to the kernel function. We still have in this setting that the dimension of the phi space would be on the order of p to the q. But this is like saying we're only going to have quadratic monomials, and this is like saying we would have quadratic, but also all the linear versions and also all the 0th degree or a constant version. Okay, and then finally, we have the Gaussian kernel. Boy, daylight savings time really changed the sunlight patterns here. So with the Gaussian kernel, again, we think about it in terms of two feature vectors. Let's just say xi and xj. And the kernel function is now going to look like I'm going to start with the distance, the Euclidean distance between xi and xj, and I'm going to square it. Then I'm going to divide it by a tuning parameter or bandwidth h. Take the negative of this, and then exponentiate. This is extremely widely used. One way that we can think about this is what we're measuring when we compute the kernel function between a pair of feature vectors is how similar those feature vectors are to one another. I can often think about my kernel matrix as being akin to a similarity matrix. And so imagine that I have a whole bunch of feature vectors that I'm just drawing in this plot here. And here I'm going to have one that's xi right here. And then over here I've got another one, xj. So I'm saying that the corresponding entry in the kernel matrix, kij, is going to depend on how far away. So I can think about having like a little Gaussian bump centered around xi, and I'm seeing how far away xj is to it. And then I am looking at the opposite of that and exponentiating. So if xi and xj are closer together, then this kernel function will be larger. And if xi and xj are farther apart, this kernel function will be smaller. It'll be less similar in that sense. And this bandwidth parameter h is telling me how quickly this measure of similarity drops off or gets small as 2 points xi and xj get further and further apart. And so in each of these settings, we've got a user-defined or a tuning parameter that we have to deal with. Here, it's this bandwidth parameter h. In the polynomials, we had the polynomial degree q. And just like when we were choosing the ridge regression parameter lambda, we would use a holdout validation set to choose it. You would do something similar here. You would use a holdout validation set, data set to select your bandwidth parameter h or your polynomial degree q. The Gaussian kernel is interesting in part because the corresponding phi function has no explicit form. So really, this is a case where there's implicitly a high-dimensional feature space, and in fact, you can show that phi of x is infinite dimensional. But there's no way that we can actually just write down what that looks like explicitly, the way we did with polynomials. So this is a setting where it's totally impossible to do ridge regression or prediction using this explicit phi mapping. We are forced to use the kernel in order to get any kind of prediction using the Gaussian kernel. Are there any questions so far? Yeah.
So here for each kernel function, we're kind of implicitly defining the phi function.
That's right. For each kernel function, there is an implicit phi function. And so I'm not writing it down for the general degree q, but there is an explicit form, and it's akin to what we did with the quadratic polynomials. So it is possible to say exactly what the corresponding phi function would look like, just like we did in our example. It's not possible to do that with the Gaussian kernel. Yeah?
The reason why that we can get it to be like xi translated xj squared is that we have the square roots to as the coefficient.
Right.
And also if we need to have it to be a q to be the exponent, we also have a specific coefficients before each terms. So does it really matter? If the coefficient does not satisfy this kind of pattern, can we still call it kernel? Because when we define the function phi, I don't think we require any pattern of the coefficient.
Right. So this is a great point, and I think to frame it a little bit more broadly than you just did, I would say that there are many, phi mappings that we might be interested in for which there does not exist a kernel. So kernel functions that correspond to inner products of the phi functions, the way we set things up, there's only, there's constraints that you have to satisfy. So it's not that for any phi function there's going to be a kernel function. And so there's really some beautiful theory associated with this, what's the space of possible functions that we're thinking about here, what makes a valid kernel, where the kernel function will have, for some phi, this sort of inner product perspective underlying it. And it's beyond the scope of what we'll cover in this class. But one of the supplementary reading books for this class, which is freely available online, is Elements of Statistical Learning. And there's a link to it on the course webpage. And it has a chapter on kernel methods, and it talks a little bit more about some of the underlying theory, including things like reproducing kernel Hilbert spaces. So you're raising an excellent point. We're just not going to go into it in more depth in this course. Yeah. Yes?
So, question about the kernel function, bottom left. So every bigger than X, so K is going to be bigger than I rows and J columns. So what do you do with the extra rows and columns of K beyond that?
So the thing to remember, which maybe I think I didn't emphasize as much as I could have over here, is that this kernel matrix is n by n. So we're just looking at the pairwise similarity of every pair xi and xj. So the size of K does not depend in any way on the dimension D or the dimension P. It's just n by n. So, and the only thing that is ultimately like d-dimensional is this weight vector WR. So this is d-dimensional, this ridge regression weight vector. But if you note, when we talked about how do I make a prediction for a new test sample, I defined that prediction in terms of the weight vector, the way we have throughout this course. But then when I actually like map out what that would look like, I never explicitly have to compute that weight vector. As soon as I've got the alphas, I'm good. There's nothing more that I need to do. So all my computations are based on computing the kernel function and looking at, similarities between pairs of feature vectors using the kernel function. Does that answer your question?
I still quite get it. Because how's phi transpose? That's going to be a, right, I see.
Yeah, no, this is fine. It takes a while, and it took me a while too. So this is n by p, and then once we do the transpose, p by n. So the product is just n by n. D. So all of the inner products in here are canceling out the d dimensions, so we just have something that's n by n. So if you're in a setting where, you want to, say, work with really high-order polynomials so that d is really big, but n is relatively small, then this is great. You start to run into trouble, though, if n is huge, right? If we think about the training data sets that are being used today to train generative models, for instance, or ImageNet, right? They're high dimensional, but also the number of training samples can be in the millions, hundreds of millions, billions, etc. And so now forming that kernel matrix, which is n by n, no longer sounds quite as appealing. So a lot of work has gone into making this more efficient, coming up with approximations to that kernel matrix so that I don't have to look at every pair of training samples, which can be a huge number of pairs. There are some kind of key trade-offs if we think about kernel methods versus neural networks. With neural networks, we're going to talk about how we train those in, I think, next week, depending on how slowly I move. We just process one training sample at a time. Whereas here we have to look at every pair of training samples. So there's a real challenge that arises when we've got huge numbers of training samples. On the other hand, there's a lot of theory and interpretability associated with kernel methods that we don't have associated with neural networks. And then finally, there's an open question of whether one is fundamentally more powerful than the other. And it's not entirely clear. So one of the things that the research community has been investigating is, are there problems that we can solve with neural networks that we cannot solve with kernel methods if we were to choose the right kernel function? And it's hard to say. That was a very long-winded answer to a very simple question. Are there any other questions? Yeah. When we talk about the reproducing kernel Hilbert space, that's something that I haven't really defined here, and we're not going to go through in this class. But the kernel function is just what I defined here. It's, corresponding to this inner product in this high dimensional feature space, and the most common ones are the polynomial and Gaussian kernels. Okay. So with that, in the lecture notes that I'll post online, I've got some nice images showing the ways in which these methods can give us much better decision boundaries. And I tried to draw one last week, but just as an example, right? Let's just imagine we're in 2D. So we've got our first feature coordinate direction and our second one. And imagine that our samples look something like this. Okay, so this is a case where trying to separate the pluses from the minuses with a straight line would be very hard, but you can imagine that some kind of polynomial decision boundary could work very well, and using kernel methods with a polynomial kernel and doing kernel ridge regression is actually going to separate them quite nicely. Okay, so, and this is very simple to implement. So now what we're going to do is we are going to go beyond kernel ridge regression, and we're going to consider, or we're going to move towards support vector machines. So to get at that, the first thing that I want to do is, now that we're 2/3 of the way through the quarter and have talked about least squares all that time, is I'm going to say, what's wrong with least squares? And the issue is this. So let's consider binary classification. So our labels y are all either -1 or +1s. And now if we think about our squared error loss, y minus xw, or equivalently y minus vw, we're just going to treat them interchangeably at this point. This is going to be the sum from I equals 1 to n, yi minus xi transpose w squared. But now what I can do is I can rewrite this somewhat differently in the setting where my y's are only +1s or -1s. Because y squared, or yi squared, is always going to be 1. Right, so this is the same as I equals 1 to n of yi squared. Well, I'm going to have the I have yi squared times yi minus xi transpose w squared, which is the same as, now I'm just going to pull the yi into this square. And so what I'm going to have is yi times yi minus xi transpose w, and multiplying through, I'm going to get 1 minus yi times xi transpose w squared. Okay, so I just have a new expression for squared error loss here that is equivalent to what we've been doing all along, in this case where all the labels are plus or minus 1, like we have in this binary classification. But now we can think about what happens in a setting like this. So I'm going to have my first feature direction and my second feature direction. Maybe I'm even doing nice linear classification, and I'm doing a great job separating my data. So here's all my negative samples, and here are all my plus samples. But now imagine I've got one plus sample way out here. So it's very far from this decision boundary. So what's happening for that sample is this quantity is going to be large. It's got the right sign because I'm correctly classifying it. But it's far from 1. And so when I take the difference between this quantity and 1 and square it, it's contributing to my loss. So I've got a sample here, which is correctly classified, but is adding to my loss. It's very counterintuitive. So let's walk through an example where this can actually create a bad classifier if we just try to minimize squared error. Okay, so in this example, we are going to say that xi is equal to the height. And so it is just a scalar. And yi is equal to +1 if the person plays basketball and -1 otherwise. And then imagine that we get 4 training samples. So I'm going to have in this example, I think this is inches of height. So the 70-inch person does not play basketball, 71-inch person does not, the 73-inch person does, and the 82-inch person does. And then what I'm going to do is I'm just going to subtract off the mean height. I'm going to center my data. So when I center it, I'm going to get -4, -3, -1, and 8. So let's just plot this now. So here on my x-axis, I've got height, and I've got samples at -4, -3, -1, and 8. And if I think about how these are labeled, I've got my negative samples, and then I've got my positive samples. So just by inspection, it's pretty clear that there exists a classifier here that will perfectly classify this data, right? If I were to just threshold right at -2, I'm perfectly classifying this data, right? But if we were to take this training data and do least squares, we actually get something different. So in particular, we've got our formula for least squares. Least squares is, remember, x transpose x inverse x transpose y. And if we plug in our training data for this example, what we get is 0.15. So what that tells us is that we should predict y hat, our predicted label, should be +1 if the observed new test height or distance from the mean is greater than 0.15 and -1 otherwise. So in blue here, we had this sort of ideal classification or decision boundary. Said if the average height is above -2, or is, I don't know, if the person's height is -2 from the mean or taller, then we should predict positive, and that works perfectly on our training data. But the least squares classifier is here, or the decision boundary. It's saying we should make a prediction based on whether someone is, 0.15 inches above the average height. So by doing least squares, we're trying to make sure that our samples are not too far from the decision boundary, even ones that are correctly classified. And so we end up pushing that decision boundary further to the right in this case than it really needs to be to perfectly classify all of our points. So this is just a simple toy example illustrating how least squares can give you bad classifiers even in easy settings where a perfect classifier exists. And so what we need then is an alternative to least squares. Any questions about this example? Yeah.
So this would not be fixed even if we had more data. We need to say -1.
Actually, it's possible that if we did have more data, then we would, because we're looking at the sum of squared errors. So if we had more data, then it is possible that the least squares decision boundary would move around for sure.
So one thing we could say it's a problem with our data collection for having outliers and not least squares.
Well, because you're right, if we had more data, then we would maybe learn a better decision boundary for sure. But at the same time, this is just highlighting a vulnerability of least squares. And when we're in one dimension, then, it's easy to say, yeah, we can just collect more data. But in higher dimensions, the amount of data that you need scales, in general, exponentially with the number of dimensions. So if I were to, it just becomes infeasible. And least squares can behave in very unusual ways and ways that are not consistent with our intuition about how things should work. Okay. Yeah. What do I mean by least squares preventing a sample?
Yeah, like why least squares trying to have all those?
So if we go back to over here, when we looked at this expression for the squared error, then let's just think about this term here for the sample where someone is 8 inches taller than the mean height. So in that case, xi transpose w, that's a large positive number, and yi is a positive 1. Okay? So we've got a large positive number here, which generally is good because this means that we have classified that sample correctly. But now we're taking that and subtracting it from 1. And so this quantity squared is going to be very big, even though we've correctly classified the point. So this outlier is trying to make sure that, it's doing exactly what we said. It's trying to minimize the sum of the squared errors, but maybe I don't want to care about how far this point is from it's giving undue emphasis to the outliers. And the toy example is illustrating that. Let's talk more generally about loss functions. And we're going to stay focused now on classification. And in particular, in general, if our label yi is +1, and we have that our feature vector xi transpose times whatever weight vector we end up choosing is greater than 0, then what this means is so remember that this is y hat. So now y hat I and yi are going to have the same sign. And when they have the same sign, it means that we are putting this sample on the correct side of the decision boundary. So predicted label is accurate. And similarly, if yi is -1 and xi transpose w is less than 0, then we're accurate. We've made an accurate prediction. Okay, so what we care about in many settings is exactly this expression that showed up in our least squares expression. What we want is that yi and yi hat, that product, we want that to be positive. That's an indicator of correct classification. Or equivalently, we want yi times xi transpose w to be positive. And so what loss functions are doing is they are ideally going to tell us something about whether we have made an accurate prediction. And so they are going to depend on this product, yi times xi transpose w. And so I'm actually going to come over here because I want to put everything on one board together. What I'm going to do is I'm going to make a plot, a better plot. And my horizontal axis is going to be yi xi transpose w, this product that we were just talking about. And the vertical axis is going to be my loss associated with whatever weight vector I choose. So we're just looking at accuracy or loss for a single training sample at this point. So what I said on the previous board is that we know that the classification is accurate when this thing is positive. So you might say, all right, then if this thing is positive, I don't want to incur any loss. I want to have 0 loss, because I've correctly classified that point. And if this product is negative, then it means I've made a bad classification, so I'm going to have a loss of 1. So this is one loss function, and we're going to call this the 0, 1 loss, or sometimes people will call it the ideal loss. And this is just equal to 1 if this product, yi xi transpose w, is negative and 0 otherwise. Okay, so this is the thing that we actually care about. This is just essentially, if we sum this across all of our training samples, this will tell us how many times we incorrectly classify points. And this is what we would like to actually minimize. The problem is that this is not differentiable. We can't do something like take the derivative and set it equal to 0 like we did with least squares. We also cannot use numerical optimization routines to find the right W. So this presents practical challenges, even though it's ideally like what we care about. So the other thing that we've considered here is quadratic. Or squared error loss. And if you recall, we were looking at 1 minus yi xi transpose w squared. And so we can now plot this on this plot here. So let's have this point here be 1. And so our quadratic loss is going to look like this. So on this side, it's great because, well, we get a little bit of extra loss here. This is a region where we're making a correct classification, but we're getting a non-zero loss. But when we're really incorrect, we get a big loss. That's great, no problem. But as we talked about earlier, and in our little toy example, you can have a correct classification, and that can still contribute a lot to your loss. So this is really problematic. Was there a question?
Yeah, I just wanted to confirm, like, are we saying that generally for all classification, we can't use our preconceived idea of what loss functions are, which is just that, like, if you have a negative yi transpose w, it's that label and other. Like, are we just saying that for generally for all classification, and not even just y plus one? I don't know if that was the
I'm not quite sure if I understand the question. I mean, maybe if I'm being really uncharitable, you could be asking, hey, we've been talking for 6 weeks now about minimizing squared error loss. Are you telling us that's all bullshit? Excuse me. All right, BS. And the answer is no. And in fact, people use least squares all the time. But it can cause unexpected behaviors. And for the most part, when people are doing classification, they do not use least squares. They use it for regression primarily. But when it comes to classification, they use other loss functions for the reasons that I'm outlining. Now, a lot of the ideas that showed up in least squares related to, the shape of the loss function, how do we minimize it, how do we think about, subspaces and that kind of stuff, all of it's relevant. So everything we learned in least squares is going to contribute to our understanding of what happens with other loss functions. This was not a waste of time. But in practice, the vast majority of the time, people use neither of these two things. They will either use hinge loss, which is what we're going to talk about now, or logistic loss, which will come up later in the quarter. Yes?
For the ideal loss function, is greater than 0. Small. For 1. If the product is...
So, all right, let's just make sure. So what I'm trying to say here is that this is a case where the sign of my inner product has one sign, or is one value, and the label has a different sign. So, like, in order for this to be less than 0, my predicted label and my true label have different signs. So it's a misclassification, so I want to have a loss. Yeah. Any other questions? Yeah.
So I think we said a long time ago that we can't, for classification, we can't, like when we're computing the loss, when we're doing like y minus y hat, or when we're doing y minus x w, we can't apply the sign function to x w for classification because it's hard to do computationally. But
Right.
is that the case? That you can't apply the sign function?
So once I've got a W, right, so all right, let me just come back over here. So the way we had set this up before is you would first learn a W, and then once you have a W, at test time, or when you deploy it, you compute X, your new X transpose times W, and then you would say your Y hat, for instance, would be equal to +1 if this inner product is positive and -1 otherwise, which is which is exactly the same as the sign of X transpose W. So once you've got a W, then you can predict the label of a new sample using the sign function. There's no problem there at all. The issue that we have is that it would be hard to say, find the W, let's say W hat ideal, which is the argument W that minimizes the sum from I equals 1 to n of the sign of XX transpose W times, or XI transpose W times YI, or something like that. If I wanted to put the sign into my loss function and then optimize over W's that are inside the sign function, that's when I have a problem. So I have no problem at test time whatsoever. It's only when I'm trying to search over W's that this is a problem. Does that make sense?
Yeah, I was asking why does that make it harder? Like why can't you?
So this sign function is just going to map to 0 or 1. So I can't, for instance, take the derivative of this and set it equal to 0 to find a minimizer. I can't, we're going to talk next week about optimization methods like gradient descent. I can't do gradient descent. It just is very hard to work with. So we don't have good methods. If you told me, oh, it's either one W vector or the other, and I just have to check which one does better, no problem. But if I've got an infinite number of W's that I'm trying to search over, which is typically the setting that we're in, I don't have tools, computationally efficient tools for doing that search. Great. Okay, so then we can also consider the hinge loss. And the hinge loss is just going to compute for us 1 minus yi xi transpose w plus. And what that means is it's going to be 1 minus yi xi transpose w if, okay, I'm going to do it this way. If I've got some quantity A plus, that's going to be A if A is positive and 0 otherwise. So I'm just going to clip A if it's negative. So I'm going to keep this if it's positive, and I'm going to clip it if it's negative. So if we plot that over here, then this quantity inside the parentheses is going to be clipped to 0 whenever the thing in parentheses is negative, or whenever this product of interest is greater than 1. So in our plot, whenever we're greater than 1, we're mapping to 0 here. And then on the other side of 1, we're just increasing linearly with this product. And so it looks like this. So there are some samples where this product is going to be positive, where we are getting a correct classification, but we're incurring a little bit of loss with the hinge loss. And when we have an incorrect classification, we're going to have even more hinge loss. But for most of the correct classifications, we are going to get 0 loss. So much better than squared error loss. And this is something now where we can compute derivatives and we can find minimizers of the hinge loss in a way that we cannot for the 0-1 ideal loss. Okay, so it kind of is designed to mimic the ideal loss, but in a way that allows us to do computation. And so basically, when we talk about support vector machines, what we're talking about is minimizing hinge loss plus this 2-norm regularizer, often using kernels. So we just put all these pieces together, and we're going to have a support vector machine. Okay, so a little bit more carefully. When we talk about the hinge loss, we are going to have the loss associated with a weight vector W is going to be the sum from I equals 1 to n of 1 minus yi xi transpose W positive parts. So whenever the thing in parentheses is negative, then we go ahead and we set it equal to 0. And We can also talk about the gradient of this loss. And I'll say a bit more about that in a second, but I'm going to, for this class, write this as the following. So it's going to be equal to an indicator of whether yi xi transpose w is less than 1 times negative yi xi. So let me unpack this a little bit. First of all, when we have this indicator function, if I write 1 and then in brackets below here, this just means 1 if A is true and 0 otherwise. And this thing here technically is not a gradient, but it's called a subgradient. Because, as you might have guessed from the plot, it's not differentiable everywhere. It's not differentiable at 1. It's differentiable everywhere else. So when we talk about doing gradient descent, often we will use this subgradient instead. Everything is fine. And I'm not going to go into a whole lot of details about that, but I just wanted to be clear that I recognize that this is not a differentiable function, but we can still use ideas related to gradient descent, which we'll talk about next week, in order to try to minimize this loss. Okay, so a couple of things. First of all, as I just mentioned, a support vector machine. With a support vector machine, we are going to minimize, with respect to weight vectors W, this hinge loss plus lambda times the weight vector 2 norms squared. So we're doing the same kind of regularization that we did with ridge regression, but instead of using squared error loss, we're now using hinge loss. Or we could do the kernel version, where we minimize, with respect to W, the sum from I equals 1 to n of 1 minus yi, and now we've got B of xi transpose W, positive part, plus lambda W. And typically when people talk about support vector machines, they often are implying that they are using a kernel here. But this corresponds to a very simple kernel. So this is what a support vector machine is doing. It's pulling all of these pieces of 2 norm regularization that we saw with ridge regression and hinge loss together. And I want to draw a picture now to illustrate what's happening. So again, let's imagine that we've got 2-dimensional features and we make a plot of some training samples here, similar to what we did before. So I'm going to have okay, so I've got some pluses and minuses, and now I am going to draw a decision boundary that looks like this. Okay, so this corresponds to some weight vector W. So now if we think about what kind of losses we're getting. So this sample way up in the corner that was causing us problems with least squares, this is going to have 0 hinge loss. This point here is incorrectly classified with this decision boundary. So it's going to have, let's just call it largish hinge loss. And this point here is correctly classified, but very, very close to the decision boundary. And so this is going to have small hinge loss. So if we go back to our picture of the loss functions over here, I had mentioned that there were some samples, like in this region over here, where we could be correctly classifying a point and still incur a little bit of hinge loss. And that's what I'm illustrating in this diagram here. I've got a sample that is correctly classified, but barely correctly classified. If it had been moved a little bit, it would be incorrectly classified. So that's going to also contribute to my hinge loss. So when I minimize the hinge loss, I'm trying to, of course, make sure that I correctly classify as many points as possible. But also, I'm trying to make sure that my training samples are far away from the decision boundary. Because I could imagine drawing an alternative decision boundary that looks, let's say, like this, where this is supposed to be correctly classified, right? So the blue and the orange lines are both perfectly classifying, they're classifying all points except one totally correctly. But we could argue that this orange one is much more susceptible to errors because a lot of the points are just barely on the correct side of the decision boundary. And so when we work with hinge loss, we're saying we really want to have a loss function that not only correctly classifies as many points as possible, but which also classifies them correctly by a large margin. So we will talk more about that and how you actually compute a support vector machine next week. Have a great weekend.